Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today, we're going to talk about acid-base reactions. This is tied to 3 learning objectives from the College Board. 1, student can translate among macroscopic observations of change, chemical equations, and particle views. LO 3.3, that the student is able to use stoichiometric calculations to predict the results of performing a reaction in the laboratory and analyze deviations from the expected results. Last one, LO 3.4, students able to relate quantities, meaning mass, volume, to identify stoichiometric relationships for a reaction, including limiting reactants. Let's talk about what is titration. And you might have done that in the lab already. It is an analytical technique to determine the molarity of an unknown solution, which we call the analyte, by reacting it with a solution of known concentration, which we call the titrant. And we also call that a standard solution because it has been standardized by a primary standard such as KHP, potassium hydrogen thiolate. Now, the equivalence point is obtained when the moles of titrant is equal to the moles of analyte. So if your moles of titrant would be the base, that's molarity times volume of the base, is equal to the moles of the analyte, the acid, molarity times volume of the acid. Therefore, you would have MAVA is equal to MBVB. The endpoint is somewhat different from the equivalence point. It is indicated by a sudden color change because of the change in the color of the indicator, but it should be very close to the equivalence point. In other words, endpoint is observed while equivalence point is calculated. When we do a titration, we have to be aware of several techniques. 1, we must check the tension of the stopcock to make sure it is not too tight or not too loose so that we don't lose any titrant to allow for smooth release of the titrant. And we also need to do lining to the burette for a couple times because we want to get rid of any water droplet or contaminant in the burette that would change the concentration of our solution. Now we fill the burette with titrant, and we turn the stopcock quickly to release any air bubble trapped in there because it would produce a wrong reading for the volume. Now we are going to pipette the analyte. We need to do some lining to the pipette to make sure that there's no contaminant or any water droplet will be removed from the lining. Now we add 2 to 3 drops of the phenolphthalein indicator to the solution in the flask. I usually would place a piece of white paper underneath the flask because then I can see the change in the color very accurately. Now I read the initial volume of the titrant in the burette to 2 decimal places, making sure that you are eye leveling the bottom of the meniscus when you read the volume. With my left hand manipulating the burette stopcock and the right hand swirling the conical flask, I would then titrate it to a pale pink color and then read the volume of the titrant in the burette and record it. Now rinse the flask with distilled water occasionally during the titration to make sure that all the titrant molecules are rinsed down into the flask. And be sure that you add the final few drops of the titrant very slowly so that we don't overshoot the endpoint. Here's a particulate drawing of titration. I have a burette containing the sodium hydroxide solution titrated into hydrochloric acid in the flask. And as the 2 types of ions are combined together, it forms water molecules. And at the end point, I get a pale pink color. Practice problem number 3. When 25 milliliters of sulfuric acid of unknown concentration is titrated with 0.175 molar of sodium hydroxide, I require the use of 28.30 milliliter volume. So what is the concentration of the sulfuric acid? First, we write a balanced equation. As you can see, 1 mole of sulfuric acid will be neutralized by 2 moles of sodium hydroxide to form the salt, sodium sulfate, and 2 moles of water. First, we calculate moles of sodium hydroxide. Take the molarity times volume. I get 0.00495 moles. Now, the moles of the sulfuric acid, because it's in a 1 to 2 mole ratio, I take the moles of sodium hydroxide multiplied by the factor of 1 mole of sulfuric acid over 2 moles of sodium hydroxide. I then obtain 0.000248 moles of sulfuric acid. Now then I take the mole divided by the volume of 25 milliliter. I have 0.0991 molarity. Practice problem number 4. Now I have 50 milliliter or 0.24 molar hydrochloric acid added to 110 milliliter or 0.13 molar barium hydroxide solution. What is the concentration of the excess hydrogen ion or hydroxide ion left in the solution? First, I write a balanced equation to show 1 mole of barium hydroxide will react with 2 moles of hydrochloric acid to form 2 moles of water liquid. Now let me calculate moles of hydrochloric acid, taking molarity times volume. I now have 0.0120 mole of HCl. Now that should produce 0.0120 mole of water. Now I go to the moles of barium hydroxide, which is 0.13 molar times 0.1100 liter. That would yield 0.0143 mole. And converting it into moles of water using a mole ratio of 2 to 1, I now obtain 0.0286 moles of water. I do this because I want to find out which is the limiting reactant, and based on this I can conclude that hydrochloric acid is my limiting reactant because it produces less moles of water. So now we can use the limiting reactant, HCl, or the product to determine how many moles of barium hydroxide has reacted. We take the 0.0120 mole of water produced, multiply that by mole ratio of 1 to 2, and we calculate to be 0.0060 moles of barium hydroxide reacted. Subtracting that from the given amount, we now end up with 0.0083 moles of the barium hydroxide left over. That means the leftover is the hydroxide ion, but because there are 2 moles of hydroxide ions in 1 mole of barium hydroxide, we must take the 0.0083 mole and double it times 2, divided by the total volume in the mixture. Now we have 0.104 molarity. Practice problem number 5. Oftentimes, we use titration technique to determine the molar mass of an unknown acid. Let's say this time we have a triprotic acid which contains 3 protons in an acid molecule, and we titrate it with sodium hydroxide. We want to find the molar mass of such an acid. We want to design a procedure to find the molar mass. Now, knowing this triprotic acid is a solid, so first we would weigh out like 0.2 grams of this unknown solid and dissolve it in a small amount of water in a conical flask. Now we fill the burette with our standardized sodium hydroxide solution of no molarity and add a couple drops of the indicator phenolphthalein to the conical flask. Now we record the initial volume of sodium hydroxide in the burette, and we titrate to a pale pink endpoint, and then record the final volume of the titrant sodium hydroxide in the burette. Write a balanced equation for the reaction. The triprotic acid is represented by H3A solid reacting with 3 moles of sodium hydroxide solution to yield the salt Na3A and 3 moles of water molecule. Let's design a data table to collect the data. We need to know the mass of the triprotic acid H3A, and it's about roughly 0.2 grams, and we need to know the initial and final volume of NaOH in the burette so that we can calculate the volume of NaOH titrated, and we do it in 3 trials. Now we calculate the molar mass of the triprotic acid, And let's say we use sample number 1, trial 1, as our sample calculation. We take the molarity times volume of the sodium hydroxide titrated and convert it into moles of H3A by using 1:3 mole ratio, and that yields 8.574 times 10 to the minus 4 moles of H3A. Dividing the mass of the solid by the moles, we now have 232.1 grams per mole as the molar mass from trial 1. Now we can calculate the average of 3 trials, which turns out to be 238 grams per mole. The next thing is to calculate the percent error, which is equal to the difference between the theoretical and the actual value over theoretical. And let's say theoretical is 210.14 grams per mole. Now we have calculated to be 13.3% error. Now, so what could have contributed to these percent errors? Let's look at a couple of possibilities. One, if the solid was wet to begin with and not completely dry, when we mass it would tend to be a greater mass, and therefore it will result into a calculated larger molar mass. Two, if we had some water in the burette and that did not get rid of, that would have diluted the sodium hydroxide solution. That means we need to now titrate with a larger volume of NaOH. So that would result in a larger calculated moles of NaOH and a larger calculated moles of the solid acid. And now it will reduce to the molar mass to be smaller. Lastly, I want to examine 2 kinds of oxides. One being the non-metal oxide, which will produce acid in water solution. Hence, they are called acidic anhydrides. Now, for example, if we bubble carbon dioxide into water, it will form carbonic acid. If we bubble sulfur trioxide into water, it will form sulfuric acid, which is a strong acid, therefore it's ionized into hydrogen ion and sulfuric ion because it's a strong electrolyte. Or we put solid dinitrogen pentoxide into water, it forms nitric acid, strong electrolyte, ionizes into hydrogen ion and nitric ions. Or we bubble sulfur dioxide gas into water, and now it forms sulfurous acid, which is a weak acid, not totally ionized. Or we put phosphorus 5 oxide powder, sprinkle it over distilled water, and we get phosphoric acid. Another kind of oxide is metal oxide. When we dissolve them in water, they form basic solution, therefore they are called basic anhydrides. Solid lithium oxide added to distilled water will form lithium hydroxide, strong base, therefore is completely ionized. Powder barium oxide put into water will form barium hydroxide, strong base again, completely ionized. Solid cesium oxide put into water, forming cesium hydroxide. Powder strontium oxide added to distilled water, forming strontium hydroxide, completely ionized. And solid sodium oxide added to water, forming sodium hydroxide, strong electrolyte, completely ionized. So these are just many examples that I have just run through to reinforce our understanding. To summarize today's learning, we have learned what is titration and the proper titration techniques. We have learned how to use stoichiometric relationship to calculate molarity, identify limiting reactant, and determine concentration of any ions remaining in the solution. We also designed an experiment to find the molar mass of a triprotic acid by using titration. Finally, we learned that all soluble metal oxides, they form basic solution in water, and all soluble non-metal oxides form acidic solution in water. I hope that you have found the above lesson to be helpful to you, and I welcome any comments from you because they will be extremely valuable to us. And I hope to see you again next time.